Hello everybody, I will start my today another coding practice. So in this video, I will solve this question. Most stones removed with same row or column. Okay. On a 2D plane, we place n stones at some integer coordinate points. Each coordinate point may have at most one stone. Each coordinate point may have at most one stone. Yeah. A stone can be removed if it shares either the same row or the same column as another stone that has not been removed. Okay. Given an array stones of length n, where stones is xy coordinate, represents the location of ith stone. Yep. Returns the largest possible number of stones that can be removed. I see. So I will be given the list, and each item represents the coordinate of the stone. And I will return the number of stones I can remove. Okay. And each row, I can remove the stone if there is the same row, or the same column as another stone that has not been removed. I see. So, if the stone I'd like to remove shares the same row with another stone, but not with the same, but if it doesn't share with another stone about the column, even if that I can remove. Either of row or column should be shared with another stone. Okay. So let me think. Okay, so let me think with this example. Mhm. Okay, so let me take a look with an example which is giving us the input. So this should be 0, 1, 1, 0, 1, 0, 1, 2, then 2, 1, and 2, 2. Yeah, this case. So in this case, remove stone 2, 2 because it shares the same row and row with 2, 1. So 2, 2, this can be removed because it shares the same row with 2, 1. Yes. So now this becomes empty. Then I still can remove, and it says remove 2, 1, which is this one, because this shared with, shares the same row, same column with this stone. So I can remove it. And then it says I should remove 1, 2, which is this one, because it shares the same row with 1, 0. Yes. Then I can remove stone 1, 0 because it shares with column 0, 0. Okay, this one. Then I can remove stone 0, 1 because it shares with the same row with 0, 0. Okay, and that's it. I see. So I removed 1, 2, 3, 4, 5 stones. So I will return 5. Okay, I totally understood. So, yep, I think I've understood the question statement clearly at this moment. So let me think of the algorithm. And just in case, at least there is one stone and up to 1,000 stones. Okay. So I think the brute force approach for this question is obviously, I will try every possible way I can in every possible order to remove the stones. Yep. But let me optimize a bit more. So let me think which stone should be remain. I mean, which stone should remain? Or I should say, so when I take a look at this, the given, coordinate again, so this stone enables to this stone and this stone to be removed. Yep. And for this stone, this it is possible for me to remove this or this. Yeah. I mean these two stones. And for example, for this stone, if this stone exists, I can remove this stone and also this stone. So obviously, let me think there is these three stones. In this case, if I remove this stone, there are two remaining stones and there's no way that I can delete each of them. However, if I delete this and then this, in that way, I can remove two stones and the remaining is only this one. Yeah. So that's the difference I can think about the which stone to be taken. Hmm. So my quick idea is I will mm, yeah, I will take a look how many tones. I mean, for each stone, I will take a look how many stones I can remove thanks to this stone. That kind of my variable to think. Mm, yeah. Okay, so that's one of the approach I've just come up with, even though I don't know how I can use this idea. Mm. Okay, and or maybe another approach I can think, I should say another idea I can think is so yeah. So another idea is in this row I can remove one stone because yeah, at least one. I mean, if I take a look at this column, at least one column should remain. One stone should remain in this column when I think just of the column. And also same for the each row. I can remove two column, no, one stone, at least if there is one stone here. Hmm. So I see. So one idea I've just come up with is if I decide to keep this stone in the end, which stones I can remove? So from here, I can say these rows can be removed, and also this column can be removed. Yeah, and yeah. Also, every stone which is same row as these two can be removed. This stone can be removed. Every column which is same as this stone can be removed. Every row which is in the same row as this stone can be removed. Then I can recover this and this. So which means that every stone in the same row as this one can be removed. Every column which is in the same column as this one can be removed. So I can recover them. Yep. Yeah. I think that's one of the approach I can use, idea I can use. So for example, if there is a kind of another island, which is here, let me think of this as this. So this and this never intersect, a kind of. So what I mean by they never intersect is that in either way, at least one stone in here and one stone in here should remain. Yeah. Okay. Because they don't share any row or any column. But if they share the same column like this, what happens is that they are in the same kind of island. So okay, I can remove this because of thanks to this. And also I can remove this and this thanks to this. And I can remove these stones thanks to this. And I can remove this stone thanks to this and this. And as I said, I can remove this stone thanks to this. And also I can remove this stone thanks to this. No, this. And I can remove this stone thanks to this. And I can remove this stone thanks to this. So now they're, thanks to this remaining stone, I can remove all the stones. Yeah. So I can say, so basically what I should do is a kind of traversal for each, stone. So I can think if two stones share the same row, I can think they are connected. Or if they share the same column, I can say they are connected. Yeah, and I can build the graph. And my task is how many islands there are. I mean, disjoint, areas there are in this graph. Yeah. So that's my idea. Again, let me say, towards the island, they are connected, and I can think, yeah. Let's think of one node and start deleting from it. So if I delete this stone, still it's possible because it is connected. And if I remove the stone and edge between from that stone are removed. And still there are remaining ones. And as long as I take the good order to delete those stones, I can delete all the stones except for one stone. That's my idea. Yeah. Yeah, that's because from one stone, I can visit any node in going this or this or this. I mean, going row, vertical direction, going horizontal direction. So what I should do is when I delete the nodes, I should, remove in the reversed order from that. For example, if it like this, and if I decide to start from here, I can traverse like 1, then 2, 3, 4, also 5, 6, 7. So what I should do is I remove them in the reversed order. First I remove 7, it's possible, 6, it's possible, and 5, it's possible, then 4, 3, 2. Yeah, in that way. Okay. Yep, I think this is how I can solve this question. Okay, so let me start the implementation. So I will take this as a graph, and as I said, I will build the adjacency graph from these stones. And also, I need the index for each stone because I try to number the nodes in the graph. So I can say, so in this way, each stone is, indexed. Then in the adjacency graph, I built the adjacency graph. Then my task is for each node. I will doing the DFS, so BFS. Let me do with DFS. So for each stone, I will do traversal from here. Sorry, so I should say start DFS from here. Then so let me write it quickly and I will come back to you. So okay, so let me explain. So here I counted the number of stones, and also I, I gave an index to each stone. This is a node ID. Then I built the adjacency graph. So basically, this adjacency graph, where each key is the node index and each value is the list of node indexes. So this is, with this, I can do the traversal. And in line 48, I initiated the visited set so that I don't visit the same nodes again and again in the traversal. And also I initiated isRun count, which should be incremented and returned in the end. Okay, and then now in line 51, I start do the DFS to count the runs. Yeah. So for each node, I will first check if it is visited already or not. If it is visited, it's already included in some island from others. I mean, reversed from another, node. So in that case, I will skip it. Otherwise, I can say island count should be incremented by 1 and start DFS from this node. Okay, so I will increment that. Yeah, so this is it. This is DFS. So in run 57, I push the initiates stack with the start, node index, and also I set it in the visited set. Then in run 60, while there is something in the stack, I continue the iteration. In run 61, this is the basic, typical way of doing the DFS, just like the template. So I pop out the previous node from the stack, and for each adjacency node, I revisit it. And if it's already visited, I will skip it. Otherwise, I mark it as visited, and also I append it to the stack. Okay. Now I will implement the build adjacency method. So how can I do it? So let me think. Should be like this. So I have to make sure that tones in the same row are adjacent. So what I can do? I think I will create the data structure like this. So for each row, like row 1, there's say index 0 and index 2. These tones are in the row 1. And for row 2, there's some tones like this and this and this. In that case, 0, 2 are connected and 1, 3, 4 are connected. And I will do the same for column 2 nodes. And the good thing here is that every time I append a new node into this, default dictionary, for example, if I find that there is tone number 5, which is this row 1. So when I append this, I just have to take a look at these two nodes because they share the same row 5. So then I should build the 0, 5 edge and 2, 5 edge and register it in the adjacency list. So every time I try to add the node to new, row number, I should connect that new node with existing nodes, which has the same row number. Okay, same for column. So let me start the implementation for this method. And let me do it set. Default is set. Yeah. Okay. So like this. Okay. Okay, and I will do the same for column. Wait, what am I doing? So I mean, for node in the same row column nodes, for each node, I will connect node and index. I mean, the current node index I and this node. Okay. And if this column is new key, then I will append, this I to here. Okay. I think I can, make this implementation easier with different dict. So I don't do this, I don't need to do this, but I just have to take a look at current row. Then we connect it. Then in the end, I just have to append this. So if this row is new, this part should be empty. So this should be an empty list. So there's no iteration for here. And I just have to add the node to this row to node row. Yep. Okay. Now I will return the adjacency list. Actually, the adjacency is set. Okay. Now I let execute my code. Sorry. And here it said cannot unpack non-iterable in the object. So obviously I have to use enable right here. Good. So seems like there's a mistake I made. So first thing I can do is taking a look at the adjacency list. And this is the one I showed. For this, I will take look. Oh, so this should be node 0, 2, 3, and 4 and 5. Yep. The node 0 should be connected with 1 and 2. Yes, 1 should be connected with 2, 0 and 2. No. Node 1 should be connected with 2 and 4. And node 2 should be connected with 0 and 3 only. Okay, let me take a look. Oh, this should be C. Okay. Now I will check it again. Node 1 should be connected with 0 and 4. Yes. Node 2 should be connected with 0, 3. Node 3 should be connected with 5 and 2. Yes. Oh, I see. So here I guess I run the count, but this is exactly the remaining number of tones. So I have to return n minus I run count. Good. So I accept this. I will submit my code. Great. Okay, so let me do the complex analysis. First, the time complexity. So it should be let me take a look. So when I build the adjacency list, I iterate this tone, each tone, and after that, all the operations, the const. No, it depends on how many rows there are in the, how many stones there are in the same row. So let's assume all the nodes are in the same row and there are 100 stones. In that case, when I push the first stone to the default dict, list in the default dict, there shouldn't be any, node. So it only, no connection required. And when I try to push the second stone, one connection is newly created. When I push the third stone, two connections should be created. So it should be 1 plus 2 plus 3 plus blah, 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 98 and 99, 98, and plus 100. So it should be n squared time complexity. And for this, so that is the, DFS. So basically what happened here is that I have to visit each node. So it should be O n, but also it depends on how many edges there are. Yeah. So I can say every, oh, so what I mean by is like this. I will assume that V is the number of nodes, which is n, and E is number of edges existing between nodes. So it should be n squared if all the rows stones are in the same row. In that case, as I said, n squared number of connections and edges exist. So I have to check all of them. So the reason why I have to check all the edges n squared is that sorry, in line 65, okay, so I can see it like this. So from stack, every node is pushed only once and popped out only once. And for each node, after it is popped out in line 65, I check all the edges from that node. So in that way, every node and every edge from each node are checked. So it should be V plus E, number of vertices and number of edges. In this case, it should be n plus n squared. So the time complexity should be n squared. For space complexity, so adjacency set should have n space. For key, for each of them, number value can be up to n. Or number of keys should be up to count of keys should be up to n in the case all the nodes have different row number. And number of values, number of nodes, total number of nodes in the values should be n. Yep, because each node is, two times n, because each node should be, Wait a minute. So yeah. Okay. So yeah, it should be O of n because each node should be registered to exactly one row. So the space complexity should be O of n for row to nodes and column to nodes they predict. So it should be n. And I will also think of the, nodes list, which should be up to n element. And also, I will think of the stack and visit set. For each of them, it can have up to n elements. So that's it. So in this way, I can say the space complexity should be O of n. Okay, so let me quickly wrap up on today's coding practice. So today, I solved the question, most stones removed with same row or column. So I'm giving it to the array and those are stones. And I can remove the stone if there is another stone which shares the same row or same column. And I will return the number of stones. I mean, max number of stones I can remove if I choose in the most smartest way. Okay, then for my solution, I actually took this as a graph question. So I noticed that the stones which share the same row or same column are connected in the graph perspective. And my task is counting, and all the nodes which are connected together in a one connected component. For each component, I can remove all the stones except for one remaining one. Yeah. So that's the thing I think. So that being said, I could rephrase this question. I could rephrase the remaining nodes as the number of islands in this graph. Then in that way, I could find out the number of remaining nodes. Minimum number of remaining nodes in the graph. Then I should return the total number of nodes minus minimum number of remaining nodes. In that way, I can find out the max number of stones I can remove. Yep, that's it. Okay, so I finished my today's coding practice with this. Thank you so much. Bye.